Hello everyone, I hope you all are safe and sound. In this video lecture, I shall cover frequency dispersion, which happens to be the last topic from this particular module. As before, I have provided a link to this video in our Google Classroom. I have also uploaded the slides in our Google Classroom so that you may be able to watch them on your personal devices or print them out if you wish to. The content of this lecture is part of module 3 of the electrodynamics course. This is the plan for this lecture. I shall first arrive at a simple model that describes the frequency dependence of the dielectric constant, which is essentially what is frequency dispersion. This particular model would be the baseline for all the remaining topics in this lecture. Then I shall explore the distinction between normal and anomalous dispersion. And finally, I shall use these concepts to discuss the behavior of conductors, insulators and plasmas in the presence of electromagnetic waves. So first, coming to the simple model for the dielectric constant that we are talking about. So we first start with the idea of dispersion. So what is dispersion? So it is essentially the dependence of mu and epsilon on omega. That is, it's the dependence of permittivity and permeability on the frequency. So in the absence of dispersion, what happens is, if I have a wave train of any arbitrary shape, so when I say arbitrary shape, it could be a pulse or it could be a continuous wave. So you consider any arbitrary wave train that will propagate without any distortion to its wave shape. So that's the meaning of the absence of dispersion. So in our simple model of the dielectric constant that we will consider, we will look at we will consider the anharmonic oscillations of electrons in the presence of an external electric field. And in general, this external electric field would be it's dependent on position and time. So it could be an electromagnetic wave, or it could be any other field which is depending on both position as well as time. So we will consider the anharmonic oscillations of electrons. So if I have a medium, that medium consists of lots of electrons, and these electrons are going to respond to the presence of an external electric field. So that response will be in the form of anharmonic oscillations. So why anharmonic? Because electrons, they're basically bound to the lattice, and when they're bound to the lattice, and if an external field comes, it tries to displace them from their respective positions, and there's going to be a restoring force, and the restoring force is going to bring about oscillations in the system. And of course there's going to be some damping also, which is associated with every electron, and that is going to make the oscillations die down, and then this electric field is going to drive the oscillations for a longer duration of time. So that's why we consider anharmonic oscillations of electrons. Now even if suppose the electrons are not really bound to the lattice, like for instance in the case of a metal where the electrons are essentially free, but still there is going to be some partial amount of binding of the electrons to the overall lattice structure of the metal. So these are the assumptions that we make. The assumptions are, first assumption is that the applied electric field and the local electric field, the difference between them is neglected. Then the second assumption is that the relative permeability is assumed to be all very close to 1. And third assumption is that the amplitude of oscillations is very small. So we'll see the consequence of this. The amplitude, when the amplitude of oscillations is very small, then the field E can be evaluated at the average position of the electron. And finally, the electric field, it varies harmonically with frequency omega. That means we're talking about a plain electromagnetic wave which is driving the anharmonic oscillations of the electrons in the medium. So we start with Newton's second law of motion. So Newton's second law of motion, what it says is mass times acceleration is equal to the net force. So mass into acceleration is equal to net force. In this case, the net force, it consists of 3 different forces. The first one will be a restoring force, which is going to try and bring the electron back to its equilibrium position. Next, there is going to be an electric force, because any electron in the presence of an electric field is going to experience a force. And thirdly, there's going to be a damping force. The damping force will be dependent on the velocity of the electron, with the velocity, the instantaneous velocity of the electron during its oscillation, and this is characterized by this quantity gamma. And this restoring force is characterized by this quantity omega naught. So omega naught, you could think of it as a natural frequency with which that electron is going to oscillate. So we could just refer to it as the resonant frequency of oscillation for that particular electron. So then we just collect all the R terms, that is the position, the first derivative of position and the second derivative of position. We collect them together, and then this is going to give us the mass times the acceleration plus gamma times the velocity plus omega naught square times the position, which is equal to minus E times the electric field. So this is our equation number 1. Okay, so now again, if we recollect the assumptions that we had, the assumption C, the amplitude of oscillation is small. So as a consequence of that, like I said, the electric field can be evaluated at the average position of the electron. So we can just write R is proportional to E. Then again, due to assumption number D, the electric field, it varies harmonically as e to the power minus I omega t. So if I, that means I could say that R is proportional to e to the power minus I omega t. So if I differentiate R once with respect to time, then what is going to happen is this minus I omega is going to come outside. So minus I omega e to the power minus I omega t. And differentiate once again, then another minus I omega is going to come. That minus and minus will get cancelled, but we have a I, so that will give us I square omega square. That I square is going to give us another minus sign, so we have minus omega square e to the power minus I omega t. Now we have seen that R is directly proportional to e to the power minus I omega t, so that means here we can just replace this. If you want to put a, instead of proportional, you want to put a equality sign, so all you need to do is just replace this e to the power minus I omega t with R, and the same thing here as well. So R dot, that is velocity, is equal to minus I omega R, and the acceleration will be equal to minus omega square into R. So we have R double dot, R dot, and we have R. Okay, so we just substitute this R double dot and R back in equation number 1. So plugging all these back in equation number 1, so R double dot, we have minus omega square R, and we have R dot, which is minus I omega R plus omega naught square into R. So everything has been written in terms of the position only. So we have m omega naught square minus omega square minus I omega into gamma R is equal to minus E times the electric field. So we just invert this equation and we write in terms of R. So R is equal to minus E by m times this quantity to the power minus 1, because it goes on to the other side, times E. Now over here in we call this equation number 2. In equation number 2, just to distinguish between this omega and this omega, omega naught, if you remember, it's the characteristic frequency with which this electron is going to oscillate about its mean position, and this omega comes from the harmonic dependence of the electric field. So if we have an electromagnetic wave which is traveling in the medium, that electromagnetic wave will have a frequency omega, and the frequency with which the electrons are going to oscillate, what that particular electron is going to oscillate, that frequency, that characteristic frequency will be omega naught. So that's the difference between this. So this is the frequency of the electromagnetic wave, and these are the resonant, this is a resonant frequency or the characteristic frequency of that electron. So this is our equation number 2. So now the dipole moment contribution due to the oscillations of a single electron. So I have a single electron which is oscillating, so it will contribute a dipole moment, and that dipole moment will be simply the charge times this R, so minus E times this R. So we just multiply, just substitute this R over here, and that is going to give us the dipole moment. So we are having, so this is what is happening here in equation number 3. This is the story so far. We have an electromagnetic wave which is which has got a harmonic dependence of time, which is traveling through the medium, and it is going to oscillate the electron. The electron oscillates at a characteristic frequency of omega naught, and omega is a frequency of the electromagnetic wave. And because of these oscillations, there is going to be an associated dipole moment for each oscillating electron, and that dipole moment is given by this expression, which we call it as equation number 3. Okay, so now let's try to visualize this. Okay, so we have in this case this gray circle, it represents our molecule. Okay, so we have n number of molecules such volume, so this gray circle, so we have n such gray circles in unit volume. And what are these different springs? These different springs represent each and every electron inside the molecule. Now you can see that I have represented these electrons as springs, and then we have some springs which are smaller, some springs which are longer, some springs which are wider. What is the difference? The difference is basically this. You see, the electrons, they are not going to be attached to the same kind of an environment. They are not going to lie in the same environment within the molecule. So for instance, if I take a let's say a carbohydrate molecule, so if you look at the electrons inside that molecule, each and every electron does not experience the same kind of an environment around it. So if you look, and if that electron has to oscillate n-harmonically, so that electron is going to experience different kind of environment around it. And this, if we are modeling the electron as a spring, then that will have, we need to consider different springs having different spring constants and different damping constants. Okay, so each and every spring, if it represents an oscillating electron, it will have a different characteristic frequency, and it will have a different damping constant. Now let us say that these two electrons, they have the same characteristic frequency and the same damping frequency, damping constant, and these three electrons, they have the same frequency. Of course, the frequency of this and frequency of this may be different, but these three have the same frequency and the same damping constant. Same holds good for this and this. Then what we can do is we can just group them together. We group these two electrons together and we call it group number 1. This is group number 2, this is group number 3, and this is group number 4. So in group number 1, we have 2 electrons, 3 electrons, 1 electron, and 2 electrons in group number 4. So we have formed groups of these different electrons, and each of these, what is common between the elements, between the electrons in this group? What is common is the frequency and the damping constant. So all the electrons in this group, they have a characteristic oscillating frequency of omega 1 and a damping constant of gamma 1. Same holds good for this also. All the three of them, they have the same characteristic frequency of omega 2 and damping constant of gamma 2. So in general, omega j is the binding frequency of the jth group, and gamma j is the damping constant of the jth group. Now we bring in one more quantity called as the oscillator strength. Okay, so oscillator strength we refer to as the quantities F. So this Fj is the oscillator strength of the jth group. So another basically this Fj is how strong a particular group is. So if there are three number of, in this case, which will be the strongest oscillator? The strongest oscillator here is going to be group number 2, because there are 3 such electrons, and this 3, as a result, there is going to be a stronger dipole moment which will be associated with this. So this is going to be the strongest, the most dominant one out of all these 4 groups. So that's called as the oscillator strength. So another way of looking at the oscillator strength is, it will be simply the number of electrons in the jth group, or you could just consider it as the fraction of electrons in the jth group. So let's consider this to be the fraction of electrons in the jth group. So that means in case of group 1, F1 is 2, in case of group 2, F2 is 3, F3 is 1 here, and F4 is 2 here. So now if I add all of them, then what do I get? F1, 2 plus 3 plus 1 plus 2, that will give us the number of electrons inside the molecule, and we have already defined the number of electrons inside the molecule. We have already called it as Z. So Z will be equal to simply the sum, that is F1 plus F2 plus F3 plus F4. So in other words, summation of these Fj's will give us the Z. Alright, so now like we saw here, every electron will have an associated dipole moment. Every oscillating electron will have an associated dipole moment, and that associated dipole moment is given by this. Here we had just called a characteristic frequency as omega, but in general, if we take that molecule over here, different electrons, they have different frequencies, omega 1, 2, 3, and so on. So all of them will have a different associated dipole moment. So here, this electron will have a dipole moment P1, this will have a dipole moment P2, sorry, this will have a dipole moment P1, this will also have a dipole moment P1, because this dipole moment, as we saw, it depends only on omegas and it will depend on the gamma value. So both of these will have the same dipole moment. As a result, this first group, it will have a total dipole moment of 2 into P1. This will have a dipole moment of 3 into P2, then 1 into P3 and 2 into P4. So we just replace each of them with these different dipole moments. So all you have to do is find out the dipole moment of a single electron in a particular group and then multiply it with the F value for that, the oscillator frequency, the oscillator strength for that particular group. So Pj is the dipole moment due to any electron in the jth group, and Pj in this case we can just write it like this. That's the same equation as before. So we have omega j minus omega j square minus omega square minus I omega gamma j to the power minus 1 times E. So that is going to be the dipole moment for any electron in any particular in the jth group. So the total polarization due to a single molecule. So what will be the total polarization or due to a single molecule? Will be 2p1 plus 3p2 plus p3 plus 2p4. So the total polarization due to a single molecule, that is p mol, will be simply equal to summation fj into pj. Now this pj is, we have already seen, pj is this one from equation number 3. Substitute this over here, so we have p mol to be equal to this quantity. So then the polarization of the medium. What is the polarization? Polarization is also known as the dipole moment per unit volume. So dipole moment per unit volume is simply the number of molecules per unit volume times dipole moment per molecule. So this will give us number of molecules per unit volume, multiply it with dipole moment in every molecule, so that will give us the total dipole moment per unit volume, and this would be simply equal to n times p mol, because number of molecules per unit volume is your capital N. So capital N times this quantity will give us the polarization of the medium. So plug these back in. So we have P is equal to N into E square by M times this summation times E. So that is going to be the polarization of this medium. So we'll call this equation number 5. So equation number 5 is this. Now if you consider a linear dielectric medium, we have P is equal to epsilon naught times chi E into E, which chi E is the electric susceptibility of the medium. And if you compare equation number 5 and 6, we can see that epsilon naught chi E is basically this quantity, N E square by M into this particular summation inside the brackets. So we obtain from here, we just take this epsilon naught on this side, so we get the electric susceptibility as N E square by epsilon naught M times the summation of this quantity. Now once we know the electric susceptibility, we can find out what is the dielectric constant. So dielectric constant is simply 1 plus chi E. Okay, the dielectric constant epsilon is also known as the relative permittivity, which is epsilon by epsilon naught. So the relative permittivity, which is equal to 1 plus chi E, so a factor of 1 is going to come into a picture. So we have epsilon r is equal to 1 plus N E square by epsilon naught M times this particular summation, so which we'll call as equation number 8. So this is the simple model for the dielectric constant that we are looking for, and this is the most important equation that we are going to encounter in this particular lecture. So I suggest, if you are watching this video, I suggest that you can just pause this video for a while and then just note down on a piece of paper, just note down this equation, call it equation number 8, and because we'll be referring to this again and again later on, so that it will be good for if you can just keep it in hand with you in handy, so that when we refer to it later, so you can just quickly have a look at it and just verify for yourself. So epsilon r is equal to 1 plus N E square by epsilon naught M summation over j fj omega j square minus omega square minus I omega gamma j to the power minus 1. So that's equation number 8. So moving forward, this will allow us now to distinguish between normal and anomalous dispersion. So now let's say omega j is one of the resonant frequencies of a molecule. So when omega j is when the applied frequency, that is the frequency of the electromagnetic wave, if it is less than omega j, obviously then omega j square minus omega square is going to be positive, right? Because when this is less than this, then this square minus this square will be a positive quantity. And when omega, the applied frequency, is greater than omega j, then this quantity is going to be negative. Now at low frequency, okay, at low frequency, below the smallest omega j, so when the applied frequency is less than the smallest, because you see in the molecule we'll have many different omega j's, many different characteristic frequencies. So below the smallest omega j, all the terms in the summation will contribute with a positive sign. okay, and this epsilon r is going to be positive. But as we cross more and more of these resonant frequencies, more and more of them, as we cross them, then those terms, omega j terms which we have crossed, they will contribute in this summation with a negative sign. And eventually, when the applied frequency becomes greater than the greatest omega j, then all the terms are going to contribute with a negative sign, and in that case this epsilon r will be smaller than 1. So to summarize this, when omega is less than omega j smallest, then epsilon r is positive, and when omega is greater than omega j, epsilon r will be negative, because all these terms in the summation will be negative, and in this case all these terms in the summation will be positive. So in this case it will be 1 plus, so it's greater than 1. In this case 1 minus, so it will be less than 1. So now to understand this, let's I have provided a diagram over here, so let's try to understand how this happens. So see, we can think of these omega j's as the frequencies of, let's say, radio channels. So radio channels will have different frequencies, so different radio channels, they have different frequencies. So this is one frequency of one particular molecule, one particular electron. This is the frequency of another electron. This is the frequency of another electron. So these are like your different radio channels. And this is omega. This is the frequency of the light, which of the electromagnetic wave which is passing through the medium. So this omega is like when in the radio receiver, when we tune the radio, we keep on changing the frequencies of the receiver so that we can tune ourselves to any of these different frequencies. So let's say initially this omega is less than the smallest. So in this case we are considering in this example, let's say we consider 3 different resonant frequencies, omega 1, omega 2 and omega 3. So obviously the smallest one is omega 1 and the largest one is omega 3. So if your applied frequency is smaller than the smallest, like it says, if it is omega is less than omega j smallest, that is smaller than the smallest omega j, that is it is smaller than omega 1, then this quantity omega 1 square minus omega square, this will be positive. This square minus this square will be positive. Similarly, this square minus this square will be positive. This square minus this square will be positive. So all of them will have positive terms. So all of them will make positive contributions. Now what we do is we change the frequency, we increase the frequency, and then let's say we bring the frequency somewhere over here. Now what will happen is, for this resonant frequency, applied frequency is greater than this. So as a result, omega 1 square minus omega square, this will be negative. But for this and this, they still remain positive. So these two resonant frequencies will still make positive contributions, but this will make a negative contribution. Now if you increase the frequency and increase it some more and bring it over here, now what will happen is it has crossed this and this, right? So in the previous case it had crossed this one and it gave a negative contribution. Now it has crossed 2 of these frequencies. Now these 2 will give us negative contributions, and this will still give us a positive contribution. And finally, when the omega is greater than the greatest, okay, when omega is greater than the greatest omega j, then all of them will give us negative contributions. Okay, so generally these omega j's, they are very small. This gamma j's, they are this damping constants, they are very small compared to the omega j's. So in most of the cases, in most of the frequencies, this epsilon is going to be approximately real. The dielectric constant is going to be approximately real, because as compared to the real part here, the imaginary part is negligible. So you can just neglect this one and it will be more or less real. But in the vicinity of an omega j, when you're close to one of these resonant frequencies, okay, when you're close to one of these resonant frequencies, the omega j minus omega square, for that resonance will dominate the real part of this equation number 8. Now why does that happen? You can see it's a summation, so we have many such summations. So for example, f1 into omega 1 square minus omega square minus I omega gamma j to the power minus 1 plus f2 into omega 2 square minus omega square minus, and so on. So we have many different terms, but here you can see here this quantity, it is a reciprocal, right? So when you are close to one of these omega j's, so let's say you're close to this omega j, when you're close to this one, then this quantity is the smallest, this difference is the smallest. So if this difference is the smallest, then because we are taking the reciprocal, we are taking a reciprocal of an extremely small quantity, so that quantity, that term is going to become the largest. So in whichever vicinity, whichever frequency omega is in the vicinity of whichever resonant frequency, that is the resonant frequency which will dominate the real part. So when omega becomes equal to an omega j, for that dominant term the real part will vanish, because omega is equal to omega j, so that is going to vanish, and as a result it will become large and it will become purely imaginary, because the real part has vanished and only the imaginary part is left. And gamma j, like I said, it is generally very small, so when you take the reciprocal of a small imaginary number, it's going to become large, and it's going to become, and of course it will be purely imaginary. So this is an example. So we have a plot of the real part of the dielectric constant and the imaginary part of the dielectric constant. So we have two different resonant frequencies, omega 1 and omega 2, and this is the how they vary. So when we are close to one such frequency, let's say omega 1, I'm getting closer and closer to this omega 1 frequency. So when this omega gets closer and closer, then the difference, omega 1 square minus omega square, that difference becomes smaller and smaller. So for this term is going to dominate in epsilon r, this term is going to dominate. So this is going to become smaller and smaller. So as this becomes smaller and smaller, this epsilon r is going to become bigger. And when you cross over to the other side, on the other side, let's say somewhere over here, okay, so this quantity, it is going to become, again, is going to become small, but this time it will be negative. So we are going to have a large positive and a large negative on either side of omega. And then when omega is equal to omega j, then this real part is suddenly is going to become 0. So as a result, because it's dominating, is going to become 0, and as a result epsilon r, the real part, will become equal to 1. But what happens to the imaginary part? The imaginary part is suddenly going to spike up, and the same thing will happen in the vicinity of omega 2 also. It's going to again increase and decrease, and then the imaginary part is going to suddenly spike up. So this brings us to the distinction between what is called as normal and anomalous dispersion. So normal dispersion is when this real part of epsilon r, when it increases with omega, the real part of epsilon r when it increases with omega, that's the normal dispersion. And anomalous dispersion is when the real part of the epsilon r decreases with omega. So this is your normal dispersion and this is your anomalous dispersion. So in normal dispersion, it occurs everywhere except in the neighborhood of an omega j. When at anomalous dispersion, what happens, the imaginary part of the dielectric constant, it becomes large and it becomes appreciable. And moment we have a imaginary part of the dielectric constant, it implies a dissipation of energy from the electromagnetic wave into the medium, and that's why we call it as a resonant absorption. So in this diagram, so this region, this shaded region, that's the anomalous dispersion part. Okay, so now coming to the behavior of conductors, insulators and plasmas. Just the distinction between, we'll start with the distinction and then we'll look at it in more detail. So if the medium has a negligibly small number of free electrons, then at all frequencies it will behave as an insulator. Whereas on the other hand, if it's got a appreciable amount of free electrons, then at low frequencies it will behave as a conductor, and at high frequencies it will behave as a plasma. Now let's look at that one by one. So let's first look at the low frequency limit. Low frequency limit first, I mean the trivial case when omega is 0. Omega is 0 means the electric field is not changing with time at all. That means that's the static case. Then it will be just like a normal polarized medium, and its behavior will be just the same as what you have probably done in your undergraduate course in chapter 4 of Griffiths. So I suggest you can just go through this particular chapter to know what happens in the static case where omega is equal to 0. But in the limit, as omega is not equal to 0 but omega tends towards 0, then the behavior of the medium will depend on whether the lowest resonant frequency, whether it is 0 or not. So for insulators, the lowest resonant frequency is not 0. Okay, now what do I mean by lowest resonant frequency being 0 or not? We'll see that after, in a little short while. We'll see that. Okay, so in the if the lowest omega j is non-zero, then if I put omega equal to 0, then that is the static case, then we'll have a molecular polarizability which will be given by this expression. So this corresponds to setting omega equal to 0 in equation number 8. So you have already written down equation number 8. In equation number 8, you just set omega to be equal to 0, and you can just use the Clausius-Mossotti equation. You can just refer, if you want to know what this equation is, just refer to Griffiths chapter 4 or Jerry Jackson section 4.6. So just take that equation number 8 which you had noted down over there, just put omega equal to 0 and then use that in the Clausius-Mossotti equation. That is going to give us the molecular polarizability of the medium. Now in case of conductors, now what will happen is some fraction of the electrons would be free. Okay, so if electrons are free, that corresponds to 0 resonant frequency. So suppose I have a free electron, we can just simply say that its resonant frequency will be 0. Now why does that happen? It follows like this. Okay, I'll just give you a quantitative understanding of how this happens. So suppose I have a electron which is free. Free electron implies means it does not oscillate, right? A free electron does not oscillate. Only bound electrons will oscillate, because something is bound. If something is bound, then you give some kind of a stimulus, it is going to try to come back to its equilibrium state. That's how you get oscillations. But if something is not bound, that is something is free, then it is not going to oscillate. So if something does not oscillate, then what happens is, another way of looking at it is, if something does not oscillate, alternate way of looking at it is, it will take infinite amount of time to complete one cycle, right? Oscillation means there's going to be a finite amount of time after which you're going to come back and repeat the cycle. Free, or if you're not oscillating, if you're free, then you'll take infinite amount of time to come back to complete that cycle. In other words, the time period, okay, the time period of oscillation for a free particle will be infinity. If the time period of oscillation for a free particle is infinity, frequency is inverse of the time period. So if time period of oscillation is infinity, that means its frequency must be 0. So that's why the free particles, it corresponds to 0 resonant frequency. So omega naught is equal to 0. Then we could think of it as, we can interpret this as, suppose we have a fraction f naught of free electrons. Okay, suppose out of all the electrons which are in the medium, every molecule will have some electrons which will have certain resonant frequencies. Apart from that, let's say some electrons from every molecule, let's say it has become free. So some fraction of free electrons are free, and so that means some fraction f naught have a resonant frequency of omega naught. Okay, then we can write this epsilon to be equal to this. Now how do we get it like this? Again, we go back to this same equation number 8. Okay, in equation number 8, epsilon is equal to 1 plus this. You can see here 1 plus, we have a summation, right? Now what is the summation made up of? It is made up of many terms. What are each term? Each term corresponds to one particular resonant frequency. Now out of all these resonant frequencies, one of the resonant frequencies happens to be 0. So that resonant frequency which happens to be 0, and corresponding to that resonant frequency, the fraction f, the oscillator or the oscillator strength, that we call it as f naught. Okay, so what we will do is, in this summation we'll pull out that term. Okay, in this summation we have many different terms, and one of these terms, the resonant frequency will be 0, and it will have a corresponding oscillator strength of f naught. That out of this summation, that particular term alone, we'll just pull it out of the summation, and the moment we pull it out of the summation, whatever is left together, we'll just club it together, and clubbing it together, we'll just call it as the contribution due to the bound electrons. So contribution to the bound electrons, contribution to the free electrons. So contribution to the free electrons will be that term from equation number 8 which we have pulled out of that summation, and everything else which has been left behind, we just club it together and we'll call it as epsilon b. So epsilon b is basically the contribution due to all the other oscillating dipoles. So now rest of it, because this is to the power minus 1, so we'll get 1 by omega plus I or gamma naught. So omega, this I have one of this omega I have taken common outside, and from here we can just rewrite this. All we have done is we have just multiplied, and we have just taken this I common outside, so that's why we have this gamma naught, and we had a I omega over here, and this I was in the denominator, we took it up into our numerator, so that's why this minus has become plus, so we have I times this. So here in equation number 9, we are able to write down this epsilon as a real part and as an imaginary part. So this real part is due to the contribution of the other dipoles. Now if you remember, if you look at equation number 8 again, in equation number 8, this epsilon b, like I said, what is epsilon b? In that summation we have just pulled out that one single term which corresponds to the free electrons. The remaining terms in the summation, they still are inside this epsilon b, and then we have assumed this gamma j's, they are generally they are very small, so that means this epsilon b will be approximately real. For most of the frequencies it will be approximately real. So epsilon b, we can assume it to be, we can safely assume that this is real and this is the imaginary part. So now let us go to the Ampere-Maxwell's law, which we have discussed in the classroom. So Ampere-Maxwell's law is simply curl of H is equal to J plus dou D by dou T. Here D is the electric displacement, and we'll assume here that the medium obeys Ohm's law. Obeying Ohm's law means the J can be written as J is directly proportional to E, and the proportionality constant is known as the conductivity of the medium, and this epsilon B is the normal dielectric constant of the medium. So D can be written as epsilon B into E. So we have assumed that this E has got a harmonic dependence on time. So if E has got a harmonic dependence on time, then differentiating D with respect to T, epsilon B is anyway a constant. So dou D by dou T is equal to epsilon B into dou E by dou T. So dou E by dou T, when the moment you differentiate the harmonic term, we'll get a minus I omega. So as a result, dou D by dou T is equal to minus I omega epsilon B into E. So that's equation number 13. So now all you have to do is this equation number 11 and equation number 13, which is substitute back in equation number 10. Okay, so we'll put sigma E over here and minus I omega epsilon B into E. We'll substitute over here. So substituting equations 11 and 13 in equation number 10, this will give us curl of H to be equal to this. So we take the E common and then we have this one. Now again note here we have epsilon B, which is multiplied with I. So we want to make epsilon B to be positive, because equation number 9, that's what it says. Equation number 9 says that epsilon B is approximately purely real and whatever is left is purely imaginary. So in this case epsilon B is having this is multiplied with I, so we want to make this to be real. So what we'll do is we'll just take minus I omega, we can take it outside. So that will give us epsilon B, and here we'll get an I, and then we have to divide sigma by omega. So we have epsilon B plus I sigma by omega into E. So that is your curl of H. So here what we had done is we had explicitly used the Ohm's law, and then that's how we got this sigma. So even if you don't do that and you attribute this if whatever is there on the right hand side to the medium, then this quantity inside the bracket could be just thought of as the dielectric, the permittivity of the medium. So that is your basically your epsilon. So that is already given your in equation number 9. There is epsilon omega is equal to this. So now all you have to do is just compare this equation number 9 with equation number 14. So equation number 9 said is the permittivity is equal to epsilon, the bound permittivity due to the bound dipoles plus some imaginary part, and here this is basically your permittivity, and that is equal to bound permittivity plus some imaginary part. So when you compare this, that means this imaginary part must be equal to this imaginary part, that is sigma by omega is equal to this, and when we solve this, that will give us the conductivity of the medium. So sigma by omega is this, so from here we get sigma is equal to this, and we sometimes we write it like this, Ne square by m gamma naught by f naught minus I omega by f naught. So here this is essentially the root model for electrical conductivity, which I probably you would have come across this in your course in condensed matter physics. So here f naught n is simply the number density of free electrons, and this gamma naught by f naught is known as the damping constant. This is an empirical quantity, that is it is found by measurements of the conductivity. So an example of this is, let's take copper at normal temperature and low frequency. Low frequency means omega is approximately less than 10 to the power 11 hertz. So copper at normal temperature and low frequency, the number density is 8 times 10 to the power 28, and the conductivity is measured to be this much. So this gives us the value of gamma naught by f naught to be equal to this much. So if we assume that every copper atom it contributes one free electrons, then F naught will be approximately equal to 1, because that's the fraction, right? So one free electron is contributed by each copper atom, so F naught is approximately equal to 1. So over here we have gamma naught by F naught is of the order of 10 to the power 13, right? And omega by F naught I'm taking it to be approximately 1. So omega is of the order of 10 to the power 11. So this is of the order of 10 to the power 13. This is of the order of 10 to the power 11. That means this imaginary part, it can be neglected compared to the real part. So which means that for frequencies up to this, that means this corresponds to the microwave region. So for frequencies well up to well and beyond the microwave region, the conductivity of the metals, they are real and they are independent of omega. So real and independent of omega means the current will be in phase with the fields. But beyond the infrared and higher frequencies, the sigma is going to be complex, because these two quantities, they will be comparable, so it will be complex, and it is going to vary as per with the sigma is going to vary with omega as per equation number 15. Okay, now let's have a look at the high frequency limit. So for that, we'll again go back to equation number 8. Okay, equation number 8, when the frequency is much larger than the highest omega j, okay, when the frequency is much larger than the highest omega j, then this entire term, okay, I could just neglect this quantity and this quantity, right? And as a result, this entire thing we could just say to be approximately equal to minus omega, okay, because omega is far greater than omega j, so this is neglected. Gamma is anyway going to be extremely small, and of course square of a large quantity will be far greater than that quantity itself, so this quantity also is neglected. So this quantity, entire quantity inside this bracket, will be approximately equal to minus omega square. So using this approximation in equation number 8, we get the dielectric constant to be equal to 1 plus n e square by epsilon naught m, because this entire thing, this dependence of j on this dependence of omega on j, this is gone, because this entire thing is equal to minus omega square. So this is going to come outside. So what is finally left behind inside the summation is only fj, and we know that summation of fj is nothing but z, right? We had defined it in one of the earlier slides. And so this is going to give us nz e square by epsilon naught m omega square. Okay, now you see this overall quantity, it must be dimensionless, right? If it's dimensionless, then you leave out this omega square, then whatever is left behind, nz e square by epsilon naught m, this quantity nz e square by epsilon naught m, this will have dimensions of omega, some frequency square, and that quantity is what we call as the plasma frequency. So we write it as simply 1 minus omega p square by omega square. We write it like this, where omega p square is the plasma frequency, that is nz e square by epsilon naught m, this quantity nz e square by epsilon naught m, that is for omega p. And here this nz is of course the number density of electrons in the medium, okay, and you can see from equation number 17 that the plasma frequency depends only on the number density of the electrons in the medium. So it is characteristic of the population of the charges in the medium. So from equation number 16, okay, this is your epsilon r. So epsilon r is equal to 1 minus omega square by omega p square by omega square. So multiply this throughout by omega, so we'll get epsilon r into omega square is equal to omega square minus omega p square. So that's your equation number 18. Then we know that I had discussed this again earlier in the classroom. There's a refractive index is approximately equal to under root epsilon r, and c by n is equal to omega by k. Speed of light divided by refractive index will be equal to omega by k. So if you take the square of this one, so we take the square of this, we have omega square by k square is equal to c square by n square. N square will give us epsilon r. Okay, so now you cross multiply this. So when you cross multiply, we'll get epsilon r into omega square is equal to c square k square. Okay, so comparing equations 18 and 19, we have left hand side is same, epsilon r into omega square. That means c square k square must be equal to omega square minus omega p square. So this will give us the wave number as c into k is equal to under root omega square minus omega p square. So this is known as the dispersion relation or equation for omega equal to omega of k. So omega is a function of the wave number. So for dielectrics, For dielectrics, this equation number 16, this particular equation, okay, which involves the plasma frequency, this equation, it is valid only if the frequency is much greater than the plasma frequency. In that case, if you plot the variation of ck with ck by omega with respect to omega, this is how it is going to vary. Here epsilon r will be approximately equal to 1. Epsilon r will be approximately equal to 1 because omega is far greater than this, so this will be approximately 0, so epsilon r is almost equal to 1. Also ck by omega will be, it will be tending towards 1. Okay, so ck by omega will tend towards 1. Then at omega is equal to omega p, ck by omega, when omega is equal to omega p, that's going to be ck by omega is going to be 0. So this is going to be this behavior is like as if you are having a waveguide which has got a cutoff frequency. So for dielectrics, okay, this omega p is acts some kind of a cutoff frequency. So k is always real and it varies with omega in a way which is similar to a mode which is traveling in a waveguide. Okay, and omega p we can interpret in that case as a cutoff frequency. Now, but in the case of the ionosphere and tenuous plasma, that is plasma which are produced in the lab, in that case the electrons are free and the damping is negligible. In case of the electrons are free, that is understandable. In case of ionosphere, why is the damping negligible? Because the ionosphere, the density of the ionosphere is extremely small, so it means the mean free path is very long, so the damping, so there is hardly any influence of one charge on its neighboring charge, so that's why the damping is negligible. For tenuous plasma, why it is damping is negligible? Because the temperature is extremely high. So if the temperature is high, that means the charged particles, they are highly energetic. So the moment the charged particles, they become highly energetic, so again they do not influence each other much, so in that case also the damping is negligible. So if the electrons are free, that means F naught will be approximately equal to Z, and because the electrons are free, this omega j's, they are going to be 0 for most of the j values, and the damping is negligible, so gamma j's are also going to be approximately equal to, they are also going to tend towards 0. So you plug these facts, you plug them into equation number 8 again, okay, and that will give us the dielectric constant to be equal to 1 minus nz e square by epsilon naught m to 1 by omega square. Now you can note down here, there again this is the plasma frequency, so you can again write this as 1 minus omega b square by omega square, so that's why it's known as the plasma frequency. So in such media, equation number 6, it holds good for all omega. Okay, so equation number 6, not only for this value for omega greater than omega p, it also holds good for omega less than omega p. Now what happens in the case if it is less than omega p, then in that case the wave number, because the wave number, this equation is the same in all the cases. Okay, this equation is the same on all the cases. So in case of tenuous plasma and the ionosphere, okay, if omega is less than omega p, the wave number becomes purely imaginary. If the wave number becomes purely imaginary, that corresponds to the electromagnetic wave being reflected off. So the incident waves will get reflected. Okay, so if incident waves get reflected, then those evanescent waves, those waves which manage to penetrate into the medium, they will fall off as exponentially as this. So there is going to be a constant which is known as alpha. So that is known as the attenuation constant. So in case of omega equal to 0, in the static case, the attenuation constant for plasma is twice omega p by c. So basically this alpha is that distance at which, when z is equal to alpha 1 by alpha, when z equals 1 by alpha, the field is going to become 1 by e times whatever was the incident field. Okay, so this so effectively what it says is, when omega is less than the plasma frequency, the incident waves, all the incident waves, they get reflected off the surface, and whatever goes inside, that is going to fall off, and that's going to fall off over a length which is inversely proportional to alpha. Okay, so if omega is large, that means alpha is also going to be large. If omega is large, alpha is also large, and if alpha is large, then the attenuation length will be smaller and smaller. So larger the plasma frequency, smaller will be the length over which it is going to attenuate and fall off. So it means most of the field is going to get expelled out of the plasma. So that's why it's known as a field expulsion, and this is a effect of controlled thermonuclear processes. Okay, and it is also exploited in plasma confinement. So I'll not really go into these because I think this will be covered in your course in plasma physics. Now what about metals? Okay, so metals also we'll find that the same relations hold good. Okay, because in the metals we have a large number of free electrons in a metal, so the dielectric constant we can just write it like this, that summation, because most of it, the number of free electrons are extremely large, so that summation will be just dominated by the free electrons, and you could just write this equation number 8, we could write it like this. So at high frequencies there is omega far greater than this gamma naught. Okay, so we could just neglect this over here, and this equation is going to become basically this. So this gamma naught is neglected, so we have minus I gamma, so I will get cancelled, the minus will come over here. So epsilon is approximately equal to epsilon b minus this quantity. Okay, so now over here we find that we have Ne square by m by f naught. So what we did is this f naught we brought it to the denominator, so we have m by f naught, and that we write it as m square. So we have something like this, and we notice that we could, because there is this epsilon and epsilon b and epsilon naught, they have the same dimensions. That means this entire quantity must be dimensionless. That means this quantity must have dimensions of square of the frequency. So this looks very similar to your plasma frequency, so we can again call this as the plasma frequency of the metal. So omega p square by omega square. Okay, so omega p square is square Ne square by m square into epsilon naught, and here m square, if you as we can see here, m square is simply m by f naught. So this is known as the effective mass of the electrons. This partially takes into account the effects of binding, that is because you see m is the mass of the electron, you're dividing m by a fraction. Fraction means this quantity is less than 1, right? So m divided by a quantity which is less than 1, that means this quantity, this m star, will be greater than m. So it means it is the electrons will be heavier than their normal, will appear to be heavier, will have more inertia. Okay, I should not use the word heavier. The electrons will have more inertia in this case, and the effect, and that is equivalent to saying that it feels the effect of binding, because that's obviously what is going to happen. Because in a metal the electrons are not really free, even though we said that it's a sea of electrons, the electrons are free to move in any part of the metal, but still it is moving inside a lattice, and so in the lattice it will still feel some kind of binding with the positively charged lattice. So this effect of binding is going to result in a increase in the inertia of the electrons, and this increase in the inertia of the electrons can be modeled as some kind of a effective mass. So therefore the behavior of metals is approximately similar to that of plasmas. So if the behavior of metals is similar to that of plasmas, then this, what we have seen, right, the field expulsion, right, the field expulsion that we have seen, that same thing is applicable for metals also. Okay, so if omega is much less than this omega p, okay, omega is much less than omega p, then light penetrates only to a very short distance into the metal, and most of them light gets reflected. So this probably explains why metals, they have high reflectivity at optical and higher frequencies. Okay, but at ultraviolet frequencies, metals, they suddenly start transmitting light, and this is known as the ultraviolet transparency of metals. So with this we have come to the end of this particular topic. So but we need to keep in mind that this is a classical theory. Okay, this is a classical theory, so it relies on classical physics, right? And but for a complete description of what happens inside a material, inside a medium, we need to take into account the quantum mechanical effects, because the Pauli exclusion principle, that plays a really important part to that. So for if you are more interested, you could just go through the relevant topics, relevant sections in these two books. You could go through the J.D. Jackson, so that gives you a few more examples. So this brings us to the end of this particular lecture on frequency dispersion. I have not given any assignments related to this particular lecture, Talking about assignments, I shall be making an important announcement on your Google Classroom very soon. So please feel free to discuss this topic as well as ask me any other questions that you may have. You can do so in the form of comments on our Google Classroom. Finally, keep yourself and your family safe. Hope to see you all soon. Goodbye for now.